glad you came back in such great numbers. Today we will continue the workshop, and I will just revisit a little bit what we did yesterday and what we'll cover today. So yesterday we talked about basics of statistics, we talked about the problem setup, what scenario we have, we talked about parameter estimation methods, credible and confidence intervals, and we presented various model comparison methods and ways to assess quality of your fit and various visualizations. Today we will go beyond the point source static scenario, and two talks in particular will be extended sources and calibration issues by Joern and Konrad Dennerl. The nice thing about X-ray astronomy is that we have not only for each photon energy, but also the time of arrival and the position on sky. So we can do this horizontal analysis in not just one-dimensional spectra, but also the other two, and sometimes all of them simultaneously. Yesterday we also covered lower energies and higher energies, extending the spectral range. But what we will not cover, unfortunately, in this workshop is more variability issues, and we also haven't really covered pileup very much. So there are other topics that one could discuss that we will not get to. After those two talks, we'll talk about how to combine information from multiple observations, either because you have a sample or you have a population that you're trying to understand. And at the end, I will do a little bit of a wrap-up and give you some practical pointers. So let's start with Jeremy, unless there are any urgent questions or confusions. Good. Jeremy, take it away. Number 2. Good.
Thanks very much. Yeah, so I'll be talking about fitting in more than one dimension. And I apologize for the lack of statistical rigor in this talk, so please correct me if I say anything that's too wrong. Just to note, I'm not going to be covering more complicated or specialized topics such as analyzing rating data and X-rays and things like that in 2 dimensions, just looking at plain CCD kind of data. This works. So my free laser pointer from the conference is very reliable. Keyboard. Okay. Okay, so extended sources can be complex. So the question is, how do you interpret the X-ray data and obtain physical quantities from it, such as the temperature of the gas in the galaxy cluster, metallicity, density, pressure, and so on from this extended source. You also have other extended sources such as supernova remnants, where you have complicated physics taking place. You might need to worry about the ionization timescales and velocities. And there are other sources like galaxies, or looking at the center of the galaxy, where you need to take account of the spatial information. Note these are the extreme end of the high end of the data quality that we get in X-rays. These are Chandra observations. These are also Chandra observations, but of more distant sources. These Chandra observations of the SPT sample galaxy clusters. And we get many fewer photons in the realms of hundreds to thousands. So there's quite a wide range in data quality that we would like to understand. X-rays. And with Fourier-Zeta in particular, we'll be going down to the count threshold of 50 counts. So how far down can we extend spectral analysis in that regime? So what would we like to do with the X-ray data? We want to make, for example, maps and profiles of relevant physical quantities from the data. So this is a temperature map of the Centaurus cluster. So I divided the cluster up into different spatial regions here, fit a spectral model to each of those spatial regions, and this is the resulting temperature map you get. So these are the best fitting maximum likelihood fits of the spectra for each of those spatial regions. This is a methodicity map. You would also like to get profiles. I'll be talking a bit more about this later on, physical quantities. One issue is that if you want to make one of these maps, there's no unique way to actually make one of these maps unless you have a complete 3D model for your object you're trying to model, which is very, very rare. So you have to be aware of biases you introduce when you make one of these maps by how you choose your binning and your fitting and so on. And for these profiles, you have to worry about projection effects, which I'll also mention a bit later. And when you're taking the best fitting parameters, or even stuff from an MCMC chain or some Bayesian technique, you have to be wary of taking these physical parameters and doing further modeling of them, as was discussed for these new kind of unfolded things in the previous day. For example, if you deproject your profiles, your points are no longer independent, and then if you go and then try and do some statistical analysis on those non-independent points, you might end up with something completely rubbish. So be aware of that. Be aware of what you're trying to do when you go and take your physical values that you've obtained from your spectral fitting. Okay, so problems when you're trying to interpret 2D data. How do you choose which regions to examine? Or do you try to fit some global 3D model? Do you want maps or radial profiles? How do you account for projection effects? Model selection, which I won't really go into too much. And then you've got some instrumental issues which I'll try to touch on at the end, such as the PSF, background, netting, response, chip gaps, point source removal. Okay, so some people try to avoid spectral fitting altogether. This is kind of controversial, perhaps, in this conference, just to be aware of this. If you have extremely high data quality, such as for these supernova remnants, it's common to slice up your data into energy space and just make images and things. Though you have to be careful what you're doing. If you do that, this may become more common when we get onto high quality data such as XIFU from Athena, where you can actually resolve single spectral lines. And you can even do things such as using energy bands that are sensitive to various physical effects. Though, of course, you have to be aware of what assumptions you're making when you do that. That was just an extra slide. If we go back to the spectral fitting, I'll now discuss the choice of regions. So if we want to do spectral fitting and make 2D maps of quantities, what regions do we choose? We can either choose independent spatial regions to do our spectral analysis. You can either choose by hand or use some automatic methods, which I'll briefly discuss now. Or some people actually choose overlapping regions. So you can make a map where you have you move around some kind of kernel and then do spectral fitting for each pixel. If you choose independent regions, it's far easier to treat the resulting values statistically, but if you have overlapping regions, then they're all correlated with each other, so you have to be much more careful when you interpret one of those correlated maps. So what we typically do is choose a region, extract a spectrum for that region, and you have to fit the model and then try to create maps from the parameters. So now I'll discuss some methods for making regions. Here's a bit of an old one I created rather a long time ago, back in 2001, which is when we got some of the initial first China data, which is just to bin up our pixels in our map until we have high enough or low enough fractional error on the number of counts in each of these binned up pixels. So this is kind of like a quadtree method coming from computer science point of view. So negative point of this kind of analysis, it's rather ugly. You have these blocky structures in your maps, and you get quite big steps in bin size because you're doubling each time. I probably wouldn't use this anymore. I'm just bringing it up as a method. It actually has one advantage, and this code will let you create maps where you have minimum uncertainties on ratios and various energy bands. That's quite a specialized topic. So there's a rather nice method that's come along based on Voronoi tessellation of maps from DL to Stettler. The idea is basically you take your X-ray image and you accrete, you make a bin by accreting neighbouring pixels to build up a bin until you reach some kind of signal-to-noise threshold. And you start a new bin, and you keep doing this. You end up with a bunch of kind of circular structures on top of it, connected to each other. Once you've got that, you can calculate the centroid of each of those bins, and then apply a Voronoi tessellation. So you build these tessellated structures where the centroids lie at the centres of each of these bins, and these lines basically separate the centres. And then you can repeat the process iteratively, building basically a better and better Voronoi model of the object. Once you've got these regions, you can then extract the spectrum to the mapping. So this code has quite a nice property of the bins are rather spatially compact, and it produces a fairly unbiased choice of bins around the signal-to-noise value. Though perhaps the shape is non-optimal for the object we're trying to study.
Is this so? There's a technique for binning, I believe, histograms in one of the Bayesian blocks by Scarwell, and he also extended this to 2D images, or two dimensions. And but of course he chooses a block.
Right.
And I was just curious if they're doing the same thing except for using, well, it's not the same thing because the shapes are free as well.
I don't know if it's the same.
Yeah, I would be curious if you combine that with signal, instead of using signals, you can always use the Bayesian blocks, but then have leaving the shapes free.
That might be interesting.
Yeah, that's really cool.
Yeah, combining those would be interesting. Yeah. So this is a pretty common technique. It works pretty well. And another technique is exactly on mine, which is called contour bin, which is a different approach. Which is the idea is basically based around the assumption that spectral properties of an object follow the surface brightness. And so you should be trying to choose regions that have similar levels of surface brightness when you're doing this. So, for example, you have an edge in your structure, there's likely to be a spectral change. If there's a spectral change, it's likely to be across that edge rather than perpendicular to it. So rather than, well, see what I mean? Yeah, so inside and outside, there should be different spectral properties rather than along it. So it's basically an assumption that goes into not trying to choose the bins. So the method is relatively simple. You basically adaptively smooth your image, and you grow bins, trying to grow along contours and surface brightness until you reach a signal-to-noise threshold. And then there's a geometric constraint which basically stops the bins going far too long. So it's a relatively simple method. And it produces some quite pretty-looking structures here. You can see these edges in the Centaurus cluster here are well mapped by the shape of the bins by doing this. So positive, great if your spectral properties follow the image. So if they don't, then that's going to be negative, so it's an assumption. And it can look pretty nice, I think, with the right parameters. Yeah, so negative is a possible bias in assuming this. Here's some, so that's choosing, this is choosing independent spatial regions to do your analysis. Some people do analysis where the maps they produce are not, the pixels and maps they produce are not independent to each other. So this is the idea of maybe moving a circle across your image or an ellipse, growing it or shrinking it depending on the number of characters within that, so you always have the same signal-to-noise ratio, and you fit each spectrum for each pixel. So basically you're seeing a lot of best fit results in one of these maps for each of those spectra, but they're all correlated with each other if you're within the distance of one of these circles or ellipses or something like that. So interpreting the map might be more tricky because you're looking the fluctuation, it's hard to assess the significance of the structures you see. But you can get some very nice results. Here's a map from Stephen Walker looking at cold front in Perseus. Here's a comparison between some of these methods to see what it does for a simulated data set. So here's one I did some time ago. So here's a kind of input simulation, a classical simulation of some model object. This is using my contour bin So basically, this is the surface brightness you're showing here. Showing how well the surface brightness is reproduced by the method. Here's the Voronoi tessellation. I was to say that this has the same signal-to-noise ratio threshold set for each of these methods. So they should have the same bin size and thing. And this is just the old adaptive binning technique. So, yeah, you can see the difference. And this is another recent paper by Kim et al. Where they looked at lots of elliptical galaxies. But because of the different results you get using the different techniques, they basically use every technique on every cluster. So they have a big database of maps using the different techniques. Actually, there's some difficulty actually interpreting these maps. You're seeing some nice 2D data, but it's very hard to know what the statistical uncertainty on the posterior probability distribution for each of those beta-fitting parameters is. And basically, the only solution I found is to do two-dimensional plots of these values, so you can try to assess the statistical significance. But if anyone has any better ideas, I'm open to them. Okay, so there's some alternative approaches that I'm aware of. Maybe this Bayesian blocks one would also fit in here, but there's this recent paper called Batman where they tried to do some Bayesian technique for multi-image analysis. So the idea is that you try to, I think this is using this Bayesian information. I may be wrong, I need to reread this paper, but the idea is to try to choose regions which are consistent with each other within the data with multiple images. But I'm not aware of any real analysis on X-ray data using this kind of technique. And it does have to use some heuristics when doing this kind of segmentation of the image out, because there's a very large parameter space in 2 dimensions. And so it doesn't. I think it just tries combining things and then comparing them against each other. It doesn't consider the whole realm of possibilities that you could do. So I think this is quite an unsolved problem doing this optimally.
There's a technique borrowed from geospatial statistics called, much larger, but INLA, this inverse Laplace approximation, and they applied this recently to like Muse data queues to be able to reconstruct an image from sparse information, and they compared it actually to this Batman technique, and it blew this away. I mean, they could reduce the image down to maybe 5% of the pixels, and still as long as there's correlation structure in the data, still rebuild the actual image. And they wrote an R package or an image you can apply to data.
Okay. That was the end of my discussion on binning, so I was going to discuss more about the models and the projection. So for galaxy clusters, we typically know what kind of model we want to fit, at least that's our understanding, which is a thermal model for the galaxy cluster. Here's what they look like for basically different temperatures for a Chandra-like response. So you have parameters for temperature, metallicity, redshift, emission redshift, and so on. So if you have a very complicated structure, you may have more than one thermal model within a spatial bin. And so that's an issue when you're trying to fit this data. And when you look at galaxies and supernova remnants, you may need more complicated modeling, such as the velocity structure, non-ionization equilibrium, or non-thermal components, which is quite recent. You may need to consider in your model. And this is just a slide to show you that actually in the centers of clusters you might need more complex model where there's highly complicated spatial structure, and then you have a lot of temperature components. So this is the Centaurus cluster again, showing by fitting multi-temperature models to each spatial region here, you can find evidence for gas at various different temperatures here. It might be indicating cooling or concentrating places. I won't go into this in any more detail, but I'll discuss projection effects now. So if we look at one of these maps, of course the object itself isn't 2-dimensional. We're not looking at 2-dimensional objects from the sky, we're looking at a 3-dimensional object from the sky. So we have to worry about the fact that the object is 3-dimensional. So the light, so if you imagine a spherical object like this, there's emission from looking along the line of sight, there's emission from each of these shells in three-dimensional space. Fortunately, basically the shells are optically thin, so we can add up the contribution for each of these going through. Though the effect of this projection can be important or cannot be important, and it really depends on what the three-dimensional structure of the object is. If you have a galaxy cluster with a steeply rising surface brightness profile, the effects of projection are much less important than if you have a flat surface brightness profile in three dimensions. So this becomes more important, more complicated in structure as well. And if you see a two-dimensional variation in some quantity, it's likely that the three-dimensional variation is stronger because you're washing away variations by adding contribution along the line of sight. So you need to worry about this when looking at your two-dimensional maps. You can try and account for this three-dimensional structure, these projection effects, if you're working with radial profiles of objects. It's harder to account for them if you're looking at 2D maps. So I'll concentrate on profiles now. So what you can do is just extract the spectra on the sky as you see them from annually on the sky and fit them. And you end up with something called projected quantities, which are some kind of emission-weighted spectrum you have along the line of sight and fitting. Of course, the model is likely to be incorrect because you've got different temperature components that you're fitting with a single temperature component. So you end up with some value that may or may not be close to the real value, depending on the structure. But what we'd really like to do is take the spectra that we see in the shells in the cluster and try to compute what happens three-dimensionally within the object. You can try and undo this projection. So what you can do in XSpec, for example, firstly, one option is to try to correct your projected quantities for projection effects. And this has been attempted, but I don't think very statistically rigorously. So I would avoid trying to do this. Maybe it's possible with simulations and things to try to do this, but it's difficult in practice. So the kind of proper thing to do is use models such as ProjCT and XSpec. Before I say that, I should actually say there's a big assumption in trying to do this, which is a geometric assumption. So you have to make some assumption when you're trying to undo the projection effects of what geometry the source is. And typically, what people do, the only thing people can do is make assumption of kind of spherical or some kind of elliptical geometry when we're doing this kind of analysis. So ProjCT and XSpec can do this. It models the projection effects, so you have a intrinsic spectrum for each of your three-dimensional shells, and it adds it along the line of sight with the right geometric factors and fits it to your data. All well and good, but it can go wrong. This is a difficult problem. For example, this is a Perseus cluster here, and you can see a temperature profile, and ProjCT results are these wildly oscillating values as you go out in radius. And this likely comes apart. I mean, in theory, this should work very well. This is forward modeling of your spectra, fitting it to the data. The model isn't good enough. There might be more than one temperature component within each of your shells, or the assumption of three-dimensional spherical cluster isn't good enough. And so the model ends up choosing one temperature component in one shell and a different one in the other, and then it oscillates because it's under and over subtracting the model each time. You can kind of avoid this by fitting inwards, so you kind of freeze you fit for this parameter, and you freeze it in, and then you fit for this, and you freeze it in, and you fit for that. And this gives you blue points, which are much more stable. So when you do that, of course, your statistical errors might be all wrong. So you have to worry about that on the fit parameters. And then you can do some not so nice things, such as this method, where you actually try to deproject the spectra. This is kind of more rather forward-fitting and backwards method, so you actually do some nasty arithmetic to your spectra and ruin all the statistical properties of your spectra. And this involves having to make some Gaussian assumptions, horrible things like that. And you end up with something that fits very nicely. method of fixing and working inwards. So this is something to be aware of when you're fitting, trying to undo projection effects. It can go very unstable. Other alternatives, you can try and fit models with mass profiles, and these are more physical-oriented models to your cluster, like assuming hydrostatic equilibrium, so you assume your cluster is in pressure equilibrium, and then you can compute the physical parameters for the shells. So this is a more physical model. Another more physical model is MB-Proj2, which is mine, which basically, rather than doing spectral analysis actually uses surface brightness profiles and narrow energy bands. So this is a non-optimal way of building your energy distribution, unfortunately, but it seems to work pretty well. So rather than check the surface brightness profiles and narrow energy bands, these are sensitive to the temperature and so on, and to the spectral model. And you assume hydrostatic equilibrium or not, and then you do some forward modeling with MTMC of your input model, which is some kind of mass profile, density profile, and you fit your surface brightness profiles. And you can end up with some density, temperature, and so on, physical properties for your cluster that way. Now I should say there's kind of fully forward modeling models. This is one called BaseX. I think this is based on multi-nest actually. Well, it uses multi-nest. But you basically have a three-dimensional model and you fit it directly to the event data. So this is quite a sophisticated analysis. So it doesn't even go to Spectra. I think it goes to full 3D data cube and fits it to that. So of course your model has to be good as well. Okay, now just in the last part I'll just briefly mention instrumentational things that you need to worry about when looking at 2D spectra. Briefly, first thing is point sources. Your 2D object is probably full of these annoying point sources. What do you do with them? Often they're just masked out in the analysis. This is quite a pretty lazy way of doing it. You need to choose some kind of threshold to cut these out. It's difficult. Or you can try and model it in the actual analysis themselves, which is pretty rarely done. It's done in the SpaceX analysis, spacing technique. So if you want to automatically detect your sources and try and cut them out, there's difficulty choosing the threshold, and often source detection routines go wrong in extended sources. They get really confused. You detect clumps or something in the cluster as some source, and so you manually have to go and chop through this. So I'd say this is pretty nasty. PSF. Of course, this means that if you look at a particular region of the sky, you can't separate it completely from the neighbouring region because it comes from the same part of the cluster. And this can vary as a function of energy and position. As long as your region size is really big compared to PSF, this problem isn't important. So, of course, if you have big, steep gradient variations and things like that, you might need to worry about this. And it's pretty difficult to account for that. But people have done it for new star results for wick examples. If you want to see an example of a better way of handling this, you can look at this result of a bullet cluster where they have to take account of PSF. Because new star has really a large PSF compared to the structures in the bullet cluster. So when you try to measure temperatures, you really need to account for the PSF. But you end up with different spatial regions which are quite mixed together, and trying to model that is stably is difficult. If you have 2D profiles, then it's much easier to account for PSF because you can use some kind of mixing model to account for the spread, the projection onto the sky. So you have the intrinsic spectra and shells in the cluster. You project this onto the sky, and then you mix together the spectra in the model for fitting. Though you have to be aware when doing this that the results can be unstable in this kind of analysis. You often end up with oscillation between the shells if you don't have a smooth physical model to fit in the data. Vignetting and response. Your ARF and your response vary over the detector. Sometimes people are very lazy and use a single ARF and response, so you should check whether that's a reasonable assumption before going ahead and doing that. So typically, difficulty difficulty is that you have some spatial region, and there may be a different path and response for each pixel within that spatial region. And so you need to somehow account for that. I mean, ideally, you probably have to fit each spatial calibration region independently and bring the results together if you want to do it statistically properly. But often people just weight together the different spatial regions with some weighting factor. It comes from a number of counts. That's a typical way people go ahead and do this. And you also need to worry about chip gaps and detector edges. Some R from response generators don't properly account for these. And Chandra used to be a bit funny when you came near the edge of the detector, so make sure they're properly included in the ARF if you want to use the normalization of your spectra. And this also comes into play if you're trying to analyze multiple data sets. Often for a big extended source, you have multiple data sets that you're trying to bring together. And these can have different pointings on the sky, and overlap in a complicated way. You might even have different data sets from Chandra or from XMM that you want to bring together. Ideally, we'd like to do a simultaneous fit of these different spectra. But then you also have to account for the varying normalizations between the instruments. That's not just coming from calibration uncertainties and things like that. It's also coming from these chip gaps and detector edges that might not overlap in the same way that you need to account for those differences in your modeling. Often people actually, if you've got the same instrument that you're looking at with different observations, you can actually try to add together the spectra. This is kind of nasty. And try to do weight the response in advance. Seems to work okay, but only if the detectors have very similar performance. And even then, be careful. This can go wrong badly if you try and add together the responses of completely different instruments. So I'd be very, very careful doing this kind of thing. And background is a complex and difficult topic, and I really don't have time to really go into this in huge detail. You can see some nice papers, such as by Melendi, for example, has done a series of papers talking about this in great detail. And background analysis is extremely important when you're looking at extended sources that have low surface brightness. In the outskirts of those objects. And there's a whole variety of different components that can go into your background and resolve points such as soft galactic components, quiescent particle background at higher energies, and then there are these nasty soft protons that you can get in the data, particularly in XMM, that can really badly affect your analysis if you don't account for these. So either you need to have an appropriate model of your background component over the detector and for the different observations you're analysing. Or people sometimes use a background event file, but this has to have much lower systematic uncertainties than what you're trying to do. So this is extremely critical for checking that the background is appropriate when doing that kind of analysis. Though it's much more critical in fainter objects. So if you're looking at the centre of the Perseus cluster, the brightest object in the sky, you don't care about the background. You can do anything. If you're looking at the outskirts of that cluster, you very much do need to care about the background. But what's particularly far easier to do, get this right if you have a source-free region in your observations. If your source fills the entire field of view, it's extremely hard to know what the background is doing. Or you can use techniques such as this XMM EPIC camera here. You notice the edges of the camera here aren't exposed to the sky, that's why they're much darker. And you can use these as comparison regions to your source to try to understand what the background is doing. And there's a package in ESAS for doing this called SAS. There's a package in the SAS software called ESAS for doing this. Maybe I missed one of the S's of ESAS there. So you have to do things their way if you use this package. It's a bit inflexible. And there's quiescent background files that you can create for XMM now with this EQBPB tool. But it's important to check that your background stuff is really correct. systematics are very important for doing this kind of analysis. And for Chandra, you have blank sky background event files. The background is less critical. You check if that's right. For most of the observatories, there are closed filter particle background event files, which are very helpful for fitting the modeling the upper part of the spectrum. And when doing analysis of extended sources and background is critical, you may actually need to optimize your energy band to make sure that you're not dominated by systematics. If the systematics on the background in one particular energy band are very high, then it may be better just to ignore that energy band and concentrate where you understand the systematics much better for that area. So optimizing the energy band is important. And I have a final slide on kind of instrumental effects, which are out of time events, which I don't think we discussed so far in the meeting. Maybe I missed to talk about it. But of course, if the event coming to detector and Joern arrives during readout of the detector, then the position of the event is wrong. And this is more or less important depending on your detector mode, how often it's being read out. And it's more or less important depending on the brightness of the source. But for example, this is a very extreme example where you can see the chart of this streak from this very bright point source here that appears on your detector. So if an extended source with a bright central region, for example, what you end up doing is making some kind of smeared structure along the readout direction in your data. Usually what happens is people try to treat this as some kind of synthetic background that they put into their spectra. This is rather nasty statistically. You take your observed data, you randomize it along your readout direction, apply some fudge factors for the time factors, and use this as some kind of background spectrum in your modeling. So this is a bit kind of nasty, but this is basically the only approach I'm aware of people use. Maybe you could try to model this if you have a very good model for your instrument. And I think that was my last slide, so that was okay.
Any questions? I do have a question. Yeah, I do have a question. Go ahead.
So for the Joern for example, how to estimate the signal to noise ratio
Oh, it's based on counts. I mean, you can use a background estimate. I think you can put into this as well. So it's signal to noise counts. I can't remember which of those signal to noise formulae that went into that calculation. But of course, the signal to noise doesn't translate automatically into getting the same uncertainty on your temperature or something like that in the spectral fit. So you're kind of aware of that.
My question was, you said you presented some techniques for getting a background from regions, maybe outside the exposed part. And then you said, but do check if the background is okay. How do you go about checking whether the background you assume is okay?
Well, if you have a spectrum from outside the source, then it's not so. Well, you can check that against some kind of background simulation or model, check it matches what you observe in the outer parts. Then you have made the assumption that it's working okay in the central parts. We try and model those in the outer parts and then use what you know about the detector. Take that model in the outer parts and use that in the central parts. But if you don't have a source-free region, it's very hard to get to check your background is correct. Which is why having the corners of the detector in X and MOS are really valuable. So you can check your model there because there's no sky photons. So you can check particle background and things are consistent with what you're applying. But it's a very difficult problem. Or you can try to use different energy bands to check your assumptions, for example. Look at the spectra and check you're not overfitting. Yeah, it's not an easy problem.
I suppose in those unexposed regions, you're also missing the cosmic X-ray background. Is that correct? Yeah.
Any more questions? So are there some more recent studies about combining data sets like SPT and X-ray, for example, or in general SC and X-ray to break the degeneracy of the deprojection?
Deprojection.
There's
different factors for the n squared. Yes, so one is I think there are some recent ones, but I remember seeing some recently. I don't remember the names of the authors. There's some, for example, the Bremsstrahlung emission you see in X-rays goes like the density squared, whereas some of the temperature signals are more like the pressure. So you can try and break the degeneracy by doing that. I think people are doing that, and so you can try to simultaneously model both data sets together with some physical 3D models of the cluster to take advantage of that.
But you don't know what the improvement is, or what the different, or how different they are from your method, for example, the results.
I'm not sure. I don't think we tried with the same clusters. And I suppose things like the problem with Planck, for example, has a rather large PSF for a signal. So if you want to try and use Planck, then maybe Vittorio would be using X-rays and Planck, for example, to try and break degeneracy. It does help a lot in the aspects.
Yes, but so the results of problem on the geometry of the cluster, and this is also degenerate with the projection that you can have, because the projection typically assumes spectral symmetry. And if it's not, it's really a problem.
Right, if it's elliptical or something, then
yes.
You're not.
But otherwise, if it's spherical, you can combine the two.
No. Maybe your average cluster it washes out. I'm not sure, depends which one it goes.
Generally, what's done is that the SC flux gives you the pressure, right? And times T. And temperature can give, X-rays can also give you the pressure. So you can assume an ICM model and fit both signals at the same time to constrain the pressure profiles. And from there, you can assume the virial theorem to the totalness, for example. Gases.
Okay. Any more comments, questions? Thank you, Joern. Now we will go to Konrad, and he will tell us. So far, we've assumed that our response, our F and R's, are somewhat God-given, and now we come to the issue: where do they come from, and what can go wrong if they're not correct, and how one might go about dealing with that.
Okay, so this is two topics which I would like to address, which have not been addressed yesterday. The first one has already been mentioned. So this is something which should not be neglected. And the second one is randomization. We will want to go into this piece. So let me start with the calibration uncertainties. And actually, this is a big topic for people working on the calibration. And it's so important that there's an international consortium which was founded a decade ago roughly, which consists of representatives of each high energy mission. They meet usually once per year and discuss calibration issues, and there are many of unresolved problems. So it's not at all that the calibration or the F and R are just there and they are given and cannot be put into question. There are uncertainties, and people working on this are well aware of these deficiencies. And this is a very nice overview which gives you an idea of the problem. So this is a beautiful supernova remnant in the SMC, where there's a beautiful XML RGS spectrum available. So we have perfect statistics, so we kind of know the truth. We know that this is a spectrum. We just take this as given and fold it through this model, through what we believe is the calibration of the individual instruments. Then we will get residuals which are more or less high. And here I have, to make it easier, highlighted the plus minus 20% error range. And you see that no matter which instrument you are picking, there's always some problematic area. So 20% is not nothing. And this is not related to the model, not related to the details of the fit, which were mentioned yesterday. It's simply calibration uncertainties. And so this is something which one has to have in mind, that this problem exists, and it becomes even more and more important with future generations, where the effective area gets higher, where the spectral illusion gets higher. You even get more and more sensitive to calibration uncertainties. Joern showed this essentially yesterday, the connection between the observed pulse height distribution, the observed spectrum, the real spectrum and the observed pulse height distribution. It can usually be modeled by a vector which essentially contains the energy dependent sensitivity of the instrument, and some matrix which deals with what the detector makes with this spectrum. And these are quite huge things. Vector is more or less simple, 3,000 elements, but the matrix, because it's two-dimensional, has millions of elements. And this also shows that it's not trivial to improve on that, although the solution has to lie somewhere in getting a suitable change, adaptation of these two entities, then we can hope that these calibration uncertainties can be minimized. I have been working on this now for many years, because I think this is very important. This is kind of the core of an instrument, to have these well calibrated for physical spectral analysis, and this is really challenging because it's so huge. You have so many parameters. We have to find the right ones and so on. Long story, would be a long talk, but let me just show you the current promising results, and also the problem which we now have. What you see here is a collection of 64 spectra, actually just the residuals to save space, from two objects. The one, so here energy is running, and here is the deviation from the model folded through the response. On top there is a supernova remnant, which we have just seen, and the bottom is an isolated neutron star, which can be, it's kind of opposite, it's a continuum, which is well characterized, very simple spectrum. Both objects have the reputation of being very reliable, and they will also be used for future calibration, for example, Rosita soon. And for these objects, many data exist, high quality data, especially from Chandra and from this RGS. And if we just take them and fold it through the response of EPIC-PN, then we get these huge residuals, especially here for this isolated neutron star. And by just changing the RMF in the same scale, you see that this can be considerably improved. If I switch forward back, you see the improvement. And this is just a replacement, the consequence of the replacement of the RMF. I'm not done yet, because I mean, this RMF has to work for many sources, not just for two. And this is still a lot of work to be done, but it is quite promising. So just keep in mind that there are calibration issues, and unfortunately, I'm not aware of any spectral fitting package which can adequately take these into account. And actually, honestly, I don't know how to do this, because I mean, for the RFIT, it might be easy, but for the RMF, the matrix, each element of the matrix has some uncertainty. It's not simple to think of an algorithm which takes. I mean, the primitive thing is you produce a random number of RMFs within the hours, but this is not as plain. It's very time consuming. So if someone has a clever idea, this is a very interesting topic that I can contribute to. historically connected to the first, to this RMF improvement, because in the process of this improvement, I wanted to make sure that the improvements I get on my local computer environment are really valid for someone else. So I asked a colleague of mine from Harvard to just check on his computer whether he gets the same results, just to be sure that I'm not running some very little stuff. He did this and he got the same result, but surprisingly, he got a much better chi-square, much better fit than I got. So this was my result, which chi-square was 1.17, and this was 0.75. And this was a bit strange. Then, of course, we checked the whole procedure and we found no difference. Even if we did exactly the same steps, we got chi-square values. And even more, when I repeated my analysis, I got yet another chi-square value. And then the suspicion came up, this must have to do something to do with how the pipeline which processes the XMM PN data works, and in some early stage it uses some randomization. And this was enough to go more into detail, because this does make a difference when I want to improve the RMF. I'm relying on these numbers and how to, this gives me feedback of how good the improvement is. So, knowing that this has to do with randomization, I did a somewhat silly experiment. I ran the same processing 100 times. So the same thing, always again. And then here you see Spectra, which came out from individual runs. There's no spectral fits. I'm just comparing the Spectra from one run with the Spectra from the other one. So this is convolved Spectra. This is the source, this is background region, and then I subtract them. And in this case, this is the maximum difference between the two Spectra. Reduced chi-square 1.17 and here 23.9. So this shows what randomization can change. So this was more or less lucky or unlucky randomization. And this is not, of course, not related to the source. This is a different source. This is a supernova. And again here, depending on the number, on the randomization details, the match is more or less good. And here you see, and then I took the average of 100 of these processing and made a fit with this average spectrum. And then you see something interesting. Of course, what we expected, the chi-square is much smaller. But you see also here that the scatter, overall the shape is very similar, but the error bar or the scatter is reduced by taking this average. So this helped improve the quality. And I have to stress, I have not multiplied photons, it's the same photons, it's just different, by this randomizing, by this averaging these individual trials, I have just kind of smoothed the random number more. And what does this mean? The problem is, why is this randomization done at all? This is a very general problem which occurs in many situations whenever you have to bind data. In the case of epic PM, we have to do this when we go from this PH8, this is for the original energy channels to the corrected channels. This step normally involves CTI and gain correction, and these corrections are small, fortunately, but so 5%, 10% or so. And this means that you stretch or compress the binning scale somewhat, and this gives less the results if you do not do randomization, and if you treat them in a very naive way by just assuming that your values are the same for everything, for example. Same problem also happens when you follow pulse profiles, when you do timing analysis, and you also have to resort your data into a different binned grid. And also in spatial, we project photons into the sky. Especially with Illucita, we have various orientations, and we have sky pixels, detector pixels. We have to rebind data. And this is a very generic problem. How should one correctly rebind data? And for this, I made a very simple experiment, numerical experiment, a random number generator. I distributed 400 counts in 10 bins. So this, you see, looks like a barcode. These are the individual random numbers, and these numbers here is what and then I increased the bin size by factor 1.4. And using the original information, which we normally don't have, so this is, so to speak, the truth. When I rebin, then this is the distribution which should come out. But in reality, we have bin data, we just have these numbers, we don't know what is inside the bins. Then apply various techniques, we can see how wrong it is to just assume that these values are located in the center of the bin, because then we get some beat things. We may get the contents of two bins falling into one bin and so on. So we get a huge scatter, which is by no means realistic. But one can do this several times. And this is now, I show you now 6 of these versions, where you can see how the result depends on this random number generator. This is more or less what happens in the processing of the source data. So depending on the details of the random number generator, you can get these or this rebinned data. And then I multiply everything by 100 and repeat it the same to simulate, try to repeat what I have done with this source processing. And then, as expected, the scatter is not to the right. That is what you have seen before, to the right is now with 100-fold numbers, then the scatter is much less, obviously. So, this is, I think, really a possibility. You can run the exams many times and take the average, but this is not in an efficient or elegant way. And I think it would be better, there is a better way in principle, but this is not implemented. But just to show you the details. So randomization, I think, is just an approximation to the probability distribution. When I compute 100 random numbers and subdivide them into 10 subpixels and assuming a homogeneous distribution, then I may get something like this. And when I do more of these trials, then it's more or less flat. I mean, and this is a distribution which is actually should be propagated, not this one, because it depends on the number generator. And for the and also for the CCPs like Rosita, we have, as Joern yesterday also mentioned, the case that one photon is not contained in one single pixel, but can be split over up to 4 pixels. And then we get other distributions which come out very nicely when I do many random number runs and come only approximately out when I have few runs. And I think this is what should be propagated, not this here. And in fact, this could be done in a not too, it would not require too much modifications. What would be necessary is to abandon the idea that we have integer PI channels. We could switch to real floating point values and could assign each event a minimum and a maximum of this PI values, and the shapes itself can be computed outside. This could be computed in the CCF photon calibration file. And so the spectrum only would need to store these two values. And then, instead of having a situation like this, which we have normally, we have integer channels, we would accumulate things like this. And so projecting them, I think, would be closer to reality. The benefit would be that, as we have seen before, the reduced chi-square, or more generally speaking, the match between the scatter of the model would be reduced, because this is an unnecessary scatter which is introduced by the randomization. And once you have less scatter, then you're also in a better position to determine the confidence intervals of your parameters you're interested in. And another benefit would be that, this is also what Joern showed yesterday in the work of extraterrestrial. You could take spectral gradients within one bin into account. So depending, let's assume this is a emission line, then it's more randomization is in my view, a limitation which is not very much justified now given the computing power that we have. Formerly this was maybe different. And that there is perhaps room for improvement at this very early stage of the data spectral fitting chain. Okay. And so to summarize, randomization is just an approximation of the right way which would be propagating probability distribution, and it may have a non-negligible effect on your spectral fits. And the recommendation for you is if you do a spectral analysis and want to be sure that when the referee comes and say, can you reproduce this result, and that you're really able to reproduce this, there's an option in XML SAS. You can set the initial value of the random number generated to a specific number, and if you just save this number, then you can really get exactly the same sequence of random numbers, and then you can produce this, your results exactly. Unfortunately, this is not a default, so you have to explicitly switch that on. Okay, this was fine.
Sorry, I have a naive question. Why does the research processing give you different results if you do it again?
Because random numbers in the computer are normally sequences, and this starting point, this is really a random number given by the time when you start the process. But from that on, the sequence is kind of predefined. And so when you do this at a different time, this initial number is set to a different value, which normally you don't know. But you can explicitly set this value, and then you get reproducible results.
So there was a study by sort of Van Dyke, and where they did something. It's not exactly the same thing. They built they used the components of Chandra, the response, and they built a Bayesian hierarchical model where they're basically putting distributions over each components of the response, and then they would use this, basically introducing the same kind of uncertainty you're proposing here, because I was really jealous. I wish we had this for GPM because we only have the components are free. But they basically would let normalizations vary on each component of the response while they're also doing the spectral fit, which propagated these uncertainties into like you're saying, into the parameter ranges of the source spectrum, and found that when you did this, your confidence intervals started encompassing the truth much more. Of course, it made them bigger, and the nice thing was that they could then get out actually PDFs of how the different components of the response looked, which they could then use in the future to do basically what you want to do is find out what the distributions of these components are. There were like 2 papers on this.
Yeah, you were also working on, I think, related to Erosita, on parameterizing the RMF, and for what you showed as well, I guess.
Actually, yes, I started with Erosita, and then I switched to
Right. So you have a way to describe various components, I guess this component shift, and the escape peak, and the main component, and the diagonal. So you have some parameterized form.
Exactly.
And I suppose, Michael, if we three sit together, we could kind of figure out how to fit everything somewhat simultaneously, and maybe that could then become a more general method. Because, yeah, as you said, it is a high-dimensional problem, but with tools like STAN, maybe we could solve it, of course, if the model is simple, like in this neutron star.
Well, the main problem at the moment is not so much the algorithm, it's finding source spectra which are reliable. I mean, these 2 are fine, but it's not just 2. And the others are either time variable or have some other problems. So just finding an X-ray source where you know the spectrum is not trivial at all.
Something when people have actually
also talked to IHF. I told them. I'm not sure they did.
Yeah, thank you for telling them, because this is important, that this information.
Yeah, I mean, I sent Anna to Matteo.
Yeah, that's
she actually went.
Okay, good. Yeah.
But it's happening, and it's like I think a lot of people are getting aware of that, especially like people who are actually coming from theory and then realizing, oh.
Joern was first.
Just a question. I missed some of the talk yesterday. But, if we want to fit a spectrum, should we be fitting the single, doubles, and triples separately with separate response matrices?
That would be the correct. I mean, this is similar to what you mentioned at the end. This is kind of different instruments. I mean, when we have singles, we have a different response than from the others, but they are very similar. I think from many cases, the calculated statistics forces you to combine them, and it's actually things and doubles. I think the others are very negligible. So I think it depends. The answer depends on the statistics. When you can afford it to fit them separately, do it. But otherwise, you have no choice.
You might get a bit more spectral resolution if you do that.
Yeah, I mean, you're combining data of different spectral resolution, and normally you do this not separately, but put them all together. But maybe that is not a big effect. That's an interesting question. Also, because we have now 7 detectors for Rosita, whether that doesn't fit them individually or combine them. Many possibilities.
This calibration collaboration, are there like products that come out of this, or papers, and the results public?
Yeah. I mean, what I showed at the beginning, this is a web page, and there are links to the papers which are published. So if you just Google for check International Consortium, then you should get all the relevant papers.
Because it's curious to me, I mean, for Swift BAT, so slightly higher energy, and GBM and ACS on integral, if you do joint fits, you can find that the spectrum between Swift BAT and GBM are like perpendicular to each other. They disagree by from anywhere between 20 to 40% in the overall flux normalization. But you never really see calibration papers between these instruments. I was like talking about this, and people, there's a paper out today that fit them together, and you know that they're disagreeing by 40% of flux. But are these issues discussed?
Yes, but I'm afraid there's no paper on this specific topic.
Yeah.
At least, I think normally each instrument is represented, so there's some.
And is it open, or is it just representatives?
I think everyone. I mean, this is a certain group, but I think it's not closed. And if someone's interested, he or she is welcome to join. So next one will be in spring in somewhere in East Coast US.
This is a question. You showed this thing with the probability distributions for each channel. I suppose you could, in theory, you just stick with PHA values and put it all into the response matrix, all the corrections, rather than so you just take the measure value in the Spectra and put everything into the response matrix.
Quite sure. So, the first thing is
there's no randomization. Just take the measure value.
Well, the response matrix, if it's used as there's an alternative to replace the response matrix by function, and that's easy. But as long as you have a matrix, this spin and these corrected PHA channels can have any value, because it is the RNA correction or numbers, floating point numbers which are close to 1. So you would need a very fine-tuned response matrix, or to do this by a matrix. Function is quite like that.
I also have a question. So the randomization that is done in XML and SAS, you were saying, is it the same procedure also in other instruments, like Chandra?
I don't know, but I kind of expect it. Actually, this randomization in the SAS also occurs when you project an image detector pixel onto the sky. So also there, the image which you get depends on the initial setting of this least what we try to do in Lucifer, we have floating point PI channels, which I think is an improvement. So when you bin your spectrum, you program it in the spectrum, gets a response as a parameter, and you can bin it to match the response. So it's more flexibility than the previous version itself. We have to see how this works.
I actually like your approach of running SAS several times and then you have different realizations and you do the fit on each of them. And you can average the probability distributions you get out, and that would be perfectly fine statistically, I would say.
Yeah. It's not very clever.
No, it doesn't have to be clever, but
it works.
You basically marginalize over procedure.
Yeah.
Marginalizing the software.
Yeah. Cool. Okay, thank you very much. Yes, let's take a coffee break for 10 minutes. Half past.
That's my So welcome back from the coffee break. Now we are talking about spectra with very few counts, and I will cover this very briefly because I believe spectra with very few counts are not anything special. Basically, if you have a Poisson likelihood and you understand your background somewhat well, you have some functional form for it, then doing the fitting is exactly as you would do with high count spectra. So if you think in allowed regions, you might have the normalization of your spectral component and another parameter, for example, the temperature here. And even if you have zero counts, some region of the parameter space is not allowed, like this part, because it would produce too many counts, which is ruled out by a Poisson likelihood. So you can, if you explore this parameter space and you think in allowed regions, then even if you have no data, it's still a measurement that gives you information, and your probability distribution will contain the regions that are still allowed. And if you think about it this way, and not let your, if you don't use a minimizer which tries to find the best fit, which is not very well defined at this kind of plateau, if you use something more sophisticated like MCMC, then you can solve this problem as well. I will give one example here of very few counts. So what I do here is I simulate a spectrum which has two components. One is this kind of flat component, which is from reflection, and a power law. I will keep those fixed, but decrease their normalization, and you will see them disappear into the background. So the source is getting fainter and fainter, or you have shorter and shorter exposure times. You can get it that way. And we will have a look at how the probability distribution changes as the source has fewer and fewer counts. So on the right, I will show you a plot of luminosity and obscuration that is allowed according to the data. Those are MCMC samples. So we start out fairly bright, the posterior is well constrained within a small region, but as the source becomes fainter and fainter, the allowed region becomes larger and larger, until at some point you are left with this very large region of probability that's still allowed. But still, in those cases where you basically background dominated, you have regions which are disallowed because the source would be too luminous, you would have too many counts predicted. And the probability distribution you get out here is described with the posterior Fourier chain, like from MCMC, or in this case from nested sampling. One interesting feature you see here, these points tracing out the allowed regions. Sometimes you get these two solutions, and you might think whether your MCMC algorithm can jump from one solution to the other solution, and if it can't, you might get a bias. So you might also want to test different methods, whether they are robust against that. Okay, so this was the short part about low counts. Now I want to come to a topic which we started to discuss about yesterday, which is the intrinsic distribution of parameters. For example, best fit distributions. We said if you just plot the best fit values, you're mixing the measurement errors with the population distribution. And if we really want to measure the intrinsic distribution, we want to kind of get rid of the measurement effect. And so one example here is you have some measurement with uncertainties, this, and you assume that these measurements are coming from an intrinsic distribution. So you're trying to find an intrinsic distribution, which you describe with the Gaussian, in this simple case, with the mean and the width. Okay? And what I want to show here is how to treat this problem. And in my approach, you would do the following. For each of your measurements, you would know your probability distribution, which is summarized by these error bars. And what you do is you take samples of that, more samples where there's higher probability and fewer where you're far away from the estimate. And you would have those samples. So if this is your axis x, and you have these samples, for this object you would have a whole bunch of samples. And then you do the same thing for each of your observations. And let's say you get 100 samples from each of them. And now you've built this kind of matrix which has objects in this direction and samples in this direction. Okay? And now this population distribution comes in, which tells you, assuming fixed mu and sigma, how probable it is to have the x value of any particular measurement at that value. So you apply this function at each of your samples, and the next step is, so in here now you go from x, I, j to a probability according to this distribution. Okay? And now with these probabilities, the idea is that one of these values for each object is a true one, but we don't know which. So this is a logical OR. So we sum in this direction, and then we get a probability for each object. And then we assume that this population distribution holds for each of the objects. Every object needs to be described by this. So we do, that's a logical AND, so we do a multiplication in this direction. And that gives us one single value, which is the likelihood. And now this likelihood, because we put in that particular population distribution, that likelihood is now a parameter of our population parameters. So let me show you this here in a specific example. So again, I said we generate 100 samples for each object. So we have 100 times the number of object matrix. We take this matrix of possible measurements, solutions. We apply our population distribution, and now we have this probability matrix. We apply it to each element. And then we, as I said, we sum over these samples, and then we make the product over these, over the objects. And we have this likelihood. And now we explore this likelihood surface as a function of the population parameter. So we vary what population distribution we would have. And before we do that, I want to give you a graphical explanation of what's going on. So let's say you have one measurement error here, which is described by this Gaussian, and you put your population distribution like this. What happens then effectively when you draw your samples and you evaluate the probability and sum over it, you're doing an integral of the convolution of the two. Because those tails don't overlap much, that region is fairly small. So you want probably your population distribution to be more over here, so the integral is larger. But if you have another measurement over here, then that population distribution is not a very good description. So you probably want to distribute the probability so that that integral and that integral have some reasonable values. Now I'll show you a numerical example where the intrinsic population distribution is 6 with a standard deviation of 2, and I will add measurement errors to that. So in the first case, we don't have any data, we don't have any measurements, but we can still compute this. Because we are doing a product over the objects, and we have 0 objects, the product is always 1. So the likelihood in this case is always 1, independent of the parameters, and so you have everything being allowed. Now we add the first data point, which is here, and some regions of this parameter space are already ruled out, namely those where you have a small value, but also a small dispersion. So this part of the parameter space is already ruled out by that single data point. Here is the true value. If we add another data point, we immediately rule out that there is low scatter in the population because those data points are mutually exclusive. But we still have this large region of the parameter space allowed. And if we add more and more and more data points, we are slowly going to the posterior is slowly going to the true value. And keep going here. If I again decrease the number of data points, the uncertainties increase. Now what I'm going to do is increase the uncertainties, increase the measurement error, and that will also increase the uncertainties. So increase, 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 and at some point that distribution can also be described by all samples having the same intrinsic value. That's what's shown here. So it could be that that's a true intrinsic value, and it's everything you see is just measurement error. But as you decrease the uncertainties, that sort of part of the solution goes away. And now J. Michael will. So this is a very specific case of hierarchical Bayesian models, where the idea is that you have your data, the thing you know, and then from that you derive some uncertainty on some physical parameter, for example, luminosity. But you don't know this value very well, but it's constrained by the data somewhat. And you have this for each individual object. So you have this n times. And the assumption here is that all of these intrinsic parameters that you can't directly observe are derived from some population distribution. And we are simultaneously trying to infer in hierarchical Bayesian models the population parameters, or the population distribution, and these intermediate values that we don't directly observe but are tied down by the data. So it's a way of describing population distributions. It's a very general framework, and J. Michael will give you some more examples now of this kind of approach.
this will be a broader than X-rays because a lot of the times when we talk about Bayesian modeling, we think, okay, it's just this thing where you run an MCMC with priors and everything. But Bayesian modeling actually, because it's much more than Bayes' theorem, it allows you to build very complex, detailed models for how our data and our physics actually works. Because our physics isn't single level, right? As Johannes was explaining, yes, you're measuring luminosity, but this could have other functions or other processes that are going on. You want to infer processes that go across the entire population, but also maybe down on other levels. And Bayesian modeling allows you to actually measure some of these things. And so I'll talk about a bunch of different, or a few different examples of Bayesian hierarchical modeling. Some that are quite important for physics, some that are quite important for just fitting lines. Have any of you ever done any Bayesian hierarchical modeling? Or are you familiar with any Bayesian hierarchical modeling? Great. Yeah. You probably are and don't realize it. But yeah, as Johannes was saying, say we have some, we'll use the word population parameter, but something what we want to infer, like say we assume that all planets come from some distribution of mass, right? But then each planet then has maybe from that mass they have some other property, and they'll each have their own distribution. And then we make some measurements, right? Some data that is coming from different objects, but those are being sampled off of those lower level distributions. So this is kind of this structure of Bayesian hierarchical modeling. Now, a lot of times, it depends on application, and none of this, every Bayesian hierarchical model is an application specific thing. There's no general rule of thumb, except for how to solve them maybe. Sometimes then you want to just group together all that data, do a sum across it, and then, okay, I try to infer the mass from that. But you destroy all this latent structure that's at lower levels. And yes, there's some power behind this because when you sum together data, you get to, you maybe make the data more powerful, it's easier to fit. But again, you lose the information. So instead, what you probably want to do, and sometimes this is called partial pooling, is build a hierarchical model. Partial pooling just kind of means that instead of combining and summing all the data together, you fit each object with its own properties, and then also try to fit this higher thing. So you partially pool the data at a higher level, and but leave each object sort of independent. And that sounds really abstract, but it is. So I will go through a couple of examples of this application and just show you, to give you an idea of how you can use this modeling to build more complex models in your own data analysis. So where do you see hierarchical modeling? Well, if you've ever looked at supernova cosmology, it is explicitly a Bayesian hierarchical model. It didn't start out that way, but these days, I think the most recent one from the Dark Energy Survey team, this code called Steve, using a code called Stan, they built a Bayesian hierarchical model to infer the cosmological parameters. But the thing is, they have individual measurements of supernovae, right? That's the data, right? How bright they are and where they are. But of course, we know that you have supernovae are sort of standard candles. You have to do this Phillips correction. I'll go through a little bit of this in a moment. So you want to fit this Phillips correction across the sample, at the same time fitting for the true luminosity of the individual objects. At the same time, fitting for the cosmological parameters. Now, if you, in the past, what people would do is they would fix the cosmological parameters, then do another step in the fit and fit the luminosity relationship, and basically break down all this very deep structure into a single level model when they were inferring supernova cosmology. And this led to things, well, there's still lots of problems with calibration and systematics, as we know, but it led to things like unknown dispersion. They couldn't understand why are the supernovae at different brightnesses than it should be. These models actually eliminate, even though it seems like you're adding, which you are, thousands of parameters, because now each supernova has its own parameters as well as the hierarchical parameters. when you add these parameters, it does not necessarily mean your fit is more unconstrained, because that only works if, in the case where you're like adding on parameters to a polynomial in a single level. These more complex model structures actually add a really deep covariance structure and correlation structure into your fit, and can actually make there actually be way more constrained and rigid models, but they allow you to fit and exploit all of this detail that's really going on in the measurement process and the physical processes. Another example is from Imperial, where they built a hierarchical model for getting redshift distributions for photometric surveys, and they also use this to find like the highest highest redshift quasar in very weak data, but they used a lot of measurements and built a giant hierarchical model, and it made them be able to find it was a quasar redshift 7. Another hierarchical model that's quite simple, and we probably run into this very often when we're doing data analysis, and there's a very famous paper that everyone should read, is when you're fitting data with errors in both x and y direction. This is a very common problem we run across, and there are very bad ways to do this. There are methods that are heuristic, like I think there's the bisect method, where you fit in one direction and then fit in the other direction and then average together the answers. There are some heuristic approaches that you'll find in numerical recipes and are implemented in IDL, like called fit EXY, which they make some approximations and they do some things, but this paper goes through all of these methods and shows that they're quite biased. And the problem is that you actually have to form a hierarchical model. And I'll go through now a notebook just for this simple hierarchical model, something that find the right one. Using a mouse in this direction is difficult. Here we go. So this is actually on Johannes's GitHub page. We started putting together last year and then stopped some recipes for astrostatistics, just like how to do certain types of common problems. For example, fitting a straight line. And to answer, okay, your question, so to fit these types of models, hierarchical models, there's a code called STAN. That's probabilistic code. One thing that's really beautiful about it is it allows you to express probabilistic models in their native language. So you say this parameter is distributed like that parameter is distributed like this, and it does all the work of forming the posterior for you and lets you fit really complex models. So that's what I use for this, and I will go through, since this is such a simple model, how to do something like that. So fitting data in two directions, and this is online, so you don't have to worry about writing all of it down. If you generate data, yeah, it's easy to do this on the chalkboard. Coming from a line, just a straight line, where you have uncertainties not only on just how high it comes in the y direction, also on in the x direction. You can imagine that if you fix as it changes in x, the model wants to go up and down like this, right? And so there's an interdependence at a higher level for the true value of x, right? So there's a latent value that is obscured by measurement error, as well as y. And so these things become extremely correlated. And so you have to kind of write that structure in. And so as Johannes was starting to write here, another way to express a hierarchical model, well, I'll show you the standard code. It's simpler. Oh, it's not on here. Sorry. This is not. I had it saved. Okay. I won't go through this because I don't have it opened up. We can talk about the actual stand code. But the main thing is that So the problem is for any hierarchical model, like with luminosity functions, as Johannes was starting to say, you can imagine that if you have a luminosity function, right, which is just a probability distribution, simple power law. So each object is being sampled from this population, right? And it's distributed as a power law, and you get a luminosity I. Okay, but this probability distribution has a normalization for the total number of objects and some kind of index, right? You want to be able to figure out this. But maybe down here, there's an uncertainty on the luminosity that could come from other physical properties. Maybe if you're doing things like I do gamma ray bursts, they have an intrinsic luminosity, but you also measure them, the jet, at a different angle. And this can change the observed luminosity. So then you have another probability distribution that obscures that. And then you have your detector, which has Poisson uncertainties, systematics, deeper down in the structure, to where you measure your actual flux. And so all of this structure, it needs to be integrated over for you to be able to infer what the entire population is doing. Does that make sense? Now, that's a specific example of a hierarchical model, and again, to show that these have been around for some time, Thomas Loreto worked this out for population studies back in the mid-90s, realizing this is the proper way to do these types of analyses. You can extend this. I did, and Johannes, I think we'll talk about your hierarchical modeling as well. Or,
No, I'm
okay. Yeah. So a similar problem where I used hierarchical modeling is in gamma ray burst. People want to try to do. People want to understand or use gamma ray burst as a cosmological tool because they're very bright. They want to standardize the candles. They can be seen very high redshifts, so they want to use them to infer cosmological parameters. And typically, what they do is look at correlations inside of individual gamma ray bursts. So if you measure, gamma ray burst has a light curve that looks like this in time. You do time resolved spectroscopy here. You get the value of the flux and where the nu peak is. And then you plot that here, and people say, okay, well, if I can do that, they seem to be correlated in a lot of the data. If I can do this for a lot of them, then I can standardize these candles. Or standardize and figure out what this group correlation is. And then I can go back for gamma ray bursts where I don't have a redshift, and I can find out where they lie on this plane. And then I can get the redshift, and then I can do high redshift cosmology. It's very similar to trying what the Phillips relation does for supernova. The problem is that in past approaches, what people did was group the data. So they took a giant sample of time resolved spectroscopy, they grouped them all onto this plane, and they just fit a global correlation. That assumes that intrinsically gamma ray bursts are some kind of standardizable candle. But if instead you fit each one of these lines individually, and you say, okay, there's some group correlation, so we forget about this being a luminosity function for a moment. You say there's some group correlation, but maybe each individual supernova has its own correlation with its own normalization and its own slope. And then you fit the individual correlations, but they talk to higher level parameters about the group correlation. If they're standardizable candles, all of this will collapse and grouping the data would work in the first place. The problem is, what you find out when you do these types of hierarchical fit is that they aren't part of a group correlation. So if you, by grouping the data, you actually destroy the latent information and the latent structure in this hierarchical model, and you get a biased answer for the redshift. And so you can actually go back and check that when you do this type of hierarchical model, you get a really bad prediction for the redshift because the objects aren't standardizable, which you don't get the same answer if you group them. So this is just another example of hierarchical modeling. once you start thinking about physics problems and data analysis problems in this hierarchical structure, you find that you can do really detailed and interesting things that it's not possible when you just do things like plot things in X and Y and fit them. You can start thinking about the underlying physics in the problem, and you can actually solve the underlying physics for populations and find out, since there's all this structure, you can actually find out really interesting things about individual objects as well. At the same time while inferring population parameters. Does that make sense? It's complex because it's a very general topic, but there is some really good software like which we can talk about and link to that can help solve this. You can also, we solve this with many different Monte Carlo algorithms, but STAN is one beautiful way to do it. Yeah. Questions?
When you say that you shouldn't stack this data and then use the information intrinsic to each of the what happens if, for example, they have like correlation between those parts? Because if you use the example of the supernovae, one is independent of the another one.
That's actually not completely true. And so, like in Steve, for the supernovae example, like if you observe two supernovae in the same fields, then because of the, I always forget this word, astrometry, what is it? Figuring out the distances. Yeah, something like that. This actually introduces correlation structure between surface supernovae. And if you ignore that, you can get really the wrong answers for the brightness as well. And so, like in Steve, they built that into the model, which helped them get rid of a lot of the systematics. So the point is that these models are just as detailed as physics problem. And if you believe that you have that kind of structure in your data, you can build it in there, and then you can fit for it. I mean, you can use the same types of techniques, for example, for calibrating instruments, right? Fitting the individual spectra in each instrument, but saying, okay, they're related somehow. And then you can actually find out the relation. This is the example that I was pointing to from the Van Dyke group, what they did with Chandra. They built kind of a hierarchical model to model the response, and they said, okay, well, maybe I'm seeing different realizations of the spectra, and then they looked at this inner structure to kind of figure out the uncertainties in the response.
Any more questions? It's a very broad topic,
Yeah.
so it's difficult to present it in a very specific way.
Do you end up with lots of parameters if you have lots of objects for this kind of analysis?
Yes.
Is that a problem?
It's not. So for example, in the supernova one, I have also on GitHub like a simple example of fitting the JLE data set with a much simpler hierarchical model than what's done in Steve. So for each object, each supernova, you have about 3 or 4 latent parameters. So that's 3 or 4 times 700. Then you have the Phillips correction parameters, and then the cosmological parameters. So you have thousands. The beautiful thing about STAN is that it's, because it uses gradients, as Johannes was talking about the other day, it's not really a big problem. That you can fit tens of thousands of parameters, and it's totally fine.
Pardon me? Some other sample modeling stuff.
Yeah, you push.
No, absolutely. So Stan is using this Hamiltonian Markov chain Monte Carlo, which takes account for the gradients, and that's basically the only reason why we can solve these very high parameter problems, and other algorithms would definitely fail.
Yeah, and it's the difficulty, as Johannes was saying, is that it's its own language, and so if you want, like for example, when you do cosmology, you have to rewrite cosmology. It's very close to C, and it's Turing complete language, and they have differential equation solvers inside and all sorts of linear algebra. So I haven't found yet a problem that I can't solve in STAN, or can't write in STAN. But again, you have to, for instrument software, you're at
I would like to do this type of modeling with Fermi-Lat, but I would have to rewrite the science tools into STAN. We're working, I have my own implementation. We want to write forward folding into STAN to be able to do, for example, like fit these correlations, but all the way down to the spectral level, so you're actually hitting the Poisson data. It's not so difficult, but it's slow because there's a lot of matrix operations. But you can do a lot.
Yeah, just to point out, the reason why it's a separate language is because it does the derivatives for you, so it does the auto-diff. That's where it comes from. I just want to make a link right there to the example I was giving. So in my example, each of those has a latent parameter, but I don't solve for that because I sample it and then I do a Monte Carlo integration, and that's how I get rid of this. And actually, if you look at one of those here, you can actually see the error of the Monte Carlo integration because I have some granularity in the summing, and you see it's not perfect. So you can look out for those structures if you want this away. Also thought of two other softwares that people could use. One is what is called Hyperfit, which does the linear correlations assuming orthogonal uncertainties.
Yeah.
And you can do correlations in 2 or more dimensions. And the other one is extreme deconvolution. Have you ever used this? Is this a hierarchical model?
It's just a Bayesian hierarchical model.
Yeah, but it's a software that people could use.
Yeah.
And I think you can also have, if you have a 2D distribution of objects in some parameter space, you can have components of the population, and you can find these components. The point of deconvolving is that you actually shrink the distribution that you would see from the measurements because it separates the measurements from the intrinsic population. Like what?
Yeah, there's also, from the paper by Brandon Kelly that kind of introduced this, there's a Python and IDL program called LenMix that does the fitting in two dimensions, and it uses a hierarchical model as a background, but you should be very careful with it because it's not an extremely general approach. It's fine-tuned with a bunch of bells and whistles, and if you use the default parameters, he gets around systematics, or he built something in where he does a Dirichlet mixture of Gaussians. So he samples from a simplex and he uses Gaussians to smooth out the data, so if you have some weird things where it's not really a line. If you use the default parameters, you're not actually fitting a line, you're fitting a mixture of Gaussian likelihoods. And so you have to open up the software and make sure that you're not doing that if you don't believe your likelihood looks like this.
So coming to the closing, we still have time for discussion if you have some particular science topics that you would like to briefly state and which we can give some advice on. We definitely have some time for that. Or some more questions to any of the topics that we discussed during those 2 days. I'll give you a second to think about it. Otherwise, I will wrap up with some practical pointers. So intentionally in this workshop we did not present software tools, but rather focused on the methods that are underlying these tools. Also because we didn't want to get into language fights which don't lead anywhere. But I do want to give you a little bit of practical advice. The first one is that you can do X-ray spectral fitting correctly in any of the software packages. So there are quite a few of them. All have their pros and cons. When you go about spectral fitting, I would encourage you to state what you're doing, what your assumptions are when you're writing it up. I would also encourage you to use Poisson statistics and treat your background with some functional form and check how your background is. Funnily enough, if you talk to statisticians these days, they don't recommend you to do everything in quantitative tests, but they focus more on visualizing what you're doing. And so visualize, visualize, visualize. That can often make more sense than absolutely trusting some statistical test. I would also encourage you to show your probability distribution, your posterior distributions, and your fits in the data space. So corner plots are very nice for this. We introduced method sampling and MCMC, which are ways to do this. We also emphasized many times to do simulations to make sure that your analysis procedure is behaving like you think it is. And if you're not sure, ask for help, ask your colleagues. Some more contact points here. First, in every institute, I think there are some people who care more than the average how science is done, and they often are very motivated to help you and are glad if you ask them. There's also the Astrostatistics Facebook group where the idea is that people come with their questions if they have some problem they run into in statistics, and it's a very dynamic group. I think we get a lot of discussion what's the best way or what are different approaches, and so you're definitely welcome to ask there. We are also active on that. There's the XSpec Facebook group where not just XSpec people ask questions about how things can be done. And at MPE, you can definitely contact us, and we're happy to answer questions or try to answer questions about statistics. Did you want to say anything else about practical pointers?
Yeah, just a few more things. Yeah, I liked your point about simulations. This is something that you don't see practiced very much, but whenever, especially when you're building a statistical model or you're wanting to test something on data, one of the best things that you can do to start out with is simulate your problem. If you have your likelihood in your model, better, your priors, you can generate simulated data, and then you go and fit it, and make sure that the algorithm that you're using, whether it be maximum likelihood or some form of sampling, can actually recover the values that you put in, because that's the best case when you actually have the true model. Reality is never going to be that good, but if your algorithm can't get back what you put in the first place, you might have a very intractable problem, and or there may be an issue in your algorithm somewhere. And this should be the number one thing whenever you start out a study to do. And you learn a lot also about the structure of your data and your model that way. The other thing is, you see this in a paper followed by test. Be careful. This thing is an old technique that we don't use anymore, shouldn't use anymore. There's an entire page about how the KS test is not really a thing that we should use for data. And if you ever see this, burn the paper immediately, because this doesn't exist. People use this a lot. It's in numerical recipes, but it's actually not a statistical thing. It's a heuristic idea. So stay away from these kind of things, because with proper statistics, you can actually fit data the right way.
I just thought of one other point, which I will immediately add to the slide, which is vary your priors and assumptions. See how your result changes, which was actually also what Konrad was doing.
And so Johannes and I are working on, and David Van Dyke and Joern are working on a paper about how to do X-ray astronomy or Poisson distributions in general. So a lot of this stuff will be in there. We're going to include a lot of code, so there are examples of how to do things. While this is nice and hopefully will work out to be a useful thing to do. There's a lot of literature about this. So Van Dyke, for example, did a lot of stuff back in the late 90s, early 2000s about how to properly treat X-ray data statistically. And I really encourage you to read those papers. We're going to put together a paper list for some of these places to go, but none of this is very new. And there's some really good literature out there for how to deal with low count spectra. That exists.
Okay, so just to wrap up, I will send around the material, which includes the slides, maybe some papers you might be interested in. And we also made a video recording of the talks, so hopefully we'll maybe edit that. If any of you have experience with video editing, definitely welcome to help out there. And we will publish that as well. And I might also send you a feedback form asking you how you liked the workshop, what we could improve in the future. That helps us improve it, but also possibly say, well, we did this workshop and people liked it. And I just want to say at the end that I was very happy that this workshop was so well attended and that you all were interested and asked also many questions, and we had some discussion. It's definitely interesting for me as well to learn, for example, yesterday about the new F nu. It's important to think about these things, and also the posterior predictive checks. I definitely want to use that more. And so yeah, thank you for coming, and yeah, I hope you had a good experience.
Discussion?
Oh, yes. If there are more discussion points, if you have any things you want to bring up, please go ahead.
When you do hierarchical models, if you assume a log model for your global data structure, is it possible to introduce correlations which are not there actually in the data?
If you use the word, this is a philosophical problem, right? Is that likely your model is wrong. If you use the wrong model, you will get stuff that you get weird answers that don't make sense, especially in those highly detailed models.
And will I be able to tell that the model I'm assuming is wrong?
No. I mean, you can see that it doesn't reproduce the data, right? But we're always, this is a philosophical point. We don't know the true model of the universe, right? So anything we do is at best approximation.
So one thing you could do is try to loosen up the model and see if the data prefer some different directions, and then maybe the data tell you that your original, more strict model was not the right one. Yeah, the other common approach is to do the posterior predictive checks, visualize whether you are reproducing the data. More questions? Okay.
And also, thanks to Paul for hosting us here. Yeah.
Thank you to you two for your efforts. It was really interesting and useful thing. So thanks to both of you.